Okay, so picture this. You're sitting in a boardroom, or, maybe you're just scrolling through a news app on your phone, and someone throws a number at you. 60% of customers love our new app. Or, the average battery life is exactly 12 hours. It looks so precise.
It sounds like a fact.
Yes, like a cold, hard fact. And that is exactly the moment you should probably start getting a little nervous.
That's the trap, because we all want that certainty, right? We want the answer to be simple.
We do, but today we're unpacking why that exact number is almost always, well, an illusion. A dangerous one.
It's what's known as false precision, and it catches everyone from Netflix executives down to political pollsters.
So welcome to the deep dive. Today we are stripping away that illusion. We're digging into Chapter 8 of our source material, Confidence Intervals.
Which I know sounds like a bit of a mouthful.
It does, but the mission today is actually really cool. We're going to give you the tool that bridges the gap between just guessing and actually knowing.
We're moving from a point estimate, that single overconfident number, to an interval estimate, an honest range.
I love that phrase for it, an honest range.
Think of it as moving from overconfidence to, well, to mathematical humility. It's about admitting what you don't know so you can be really sure about what you do know.
Mathematical humility. Perfect. So let's start with the basic problem. Why can't we just know the truth? If Netflix wants to know their subscriber satisfaction, why not just ask all 230 million of them?
Ah, the census approach. It's the dream, right? If you ask everyone, you have zero error. But in the real world, for business, for science, it's almost always impossible.
And the sources break this down into 3 big walls you hit.
3 massive walls: cost, destruction, and time.
Okay, let's break this down. Cost seems like the most obvious one.
It is, but the sheer scale of it is what people miss. If you want to do a professional survey, not just, a Twitter poll, it costs money, maybe $25 to $100 per person.
Right, so even 1,000 people, that's up to 100 grand. That's a lot. But for a big company, maybe doable.
Maybe. But what if you try to do a census of your 100,000 customers? You're suddenly talking about spending $2.5 million to $10 million.
Just to find out if they like your product.
Yeah, you'd go bankrupt just trying to figure out if you're popular. It's just bad economics.
Okay, so that's cost. The second wall is destruction. This one sounded intense.
Oh, it is. It's my favorite because it's so counterintuitive.
Yeah.
Imagine you manufacture batteries or safety glass for cars. You need to prove how long they last. How do you test a battery's lifespan?
You turn it on and wait for it to die.
Exactly. You run it until it fails. It's called destructive testing. Now, if you wanted to be 100% certain about the quality of your entire inventory,
I would have to destroy my entire inventory.
good news, boss. We've confirmed with 100% certainty that every battery we made was perfect. Bad news is, we have 0 batteries left to sell.
That's a terrible business model.
It truly is. So you have to sample, you test 50, you destroy them, and you use that data to judge the 50,000 you never touched.
You literally have no other choice. Okay, and the third wall is time.
Think about medical trials. If a drug company waited to test a new cancer treatment on every single patient who might need it, it would take decades.
And people need that medicine now.
Right now.
Yeah.
The cost of waiting is measured in lives. So we take a sample, maybe 5,000 patients, and we try to extrapolate the truth for everyone from that.
Okay, so we've established we have to sample. We can only look at a slice of the pie, not the whole thing. But here's the core issue, right? The moment you only look at a slice, you introduce randomness.
Yes, that's the demon we're fighting all day. It's called sampling variability.
The source material had this urn analogy that I thought was perfect for explaining this. Can you walk us through it?
It's a classic. Imagine a giant urn with, say, 100,000 balls inside. Some red, some blue. You want to know the true percentage of red balls, but you can't count them all.
So I reach in blindfolded and I pull out a sample. Maybe 1,000 balls.
You count them up. You get 520 red balls. So
Right.
your sample tells you it's 52%.
Okay. 52%. Got it.
Now, you put them all back, shake up the urn, I step up, I reach in and grab a different handful of 1,000 balls, I count mine, and I might get 51.5%.
And if a third person does it?
They might get 52.3% or 51.8%.
So who's wrong?
Nobody. And that is the key insight. Nobody made a mistake. We just held different handfuls of reality. That wobble, that fluctuation isn't an error. It's just randomness.
But here's the thing. In the real world, you don't get to dip your hand in the urn 100 times. You usually only get to do it once.
It's exactly once.
Yeah.
Netflix runs that survey, they get a satisfaction score of 7.4, and that's it. They have no idea if they grabbed a high handful or a low one. They're just holding that one single number.
And that one number is what we call the point estimate.
Correct. The point estimate is that single pin on the map. Satisfaction is 7.4.
It sounds so definitive.
And that's what makes it dangerous. It implies you hit the bullseye. But in reality, you don't know how close that pin is to the real treasure. The point estimate just ignores all that uncertainty.
So if the point estimate is the misleading friend, then the hero of our story is the interval estimate.
That's the solution. Instead of saying satisfaction is 7.8, we say something like, we are 95% confident the true satisfaction is somewhere between 7.42 and 8.18.
Now, let me play devil's advocate here. That feels a bit vague. You know, executives want answers. If I tell my boss sales are somewhere between 1 million and 2 million, I might get shown the door.
It feels vaguer, but it's actually more honest and I'd argue more useful. It quantifies the risk. It gives you a lower bound and an upper bound. If that lower bound, say 7.42, is still good enough for your goals, you can move forward.
But if the lower bound is a complete disaster,
then you know you have a problem. The point estimate hides that risk. The interval reveals it. It's about defining the width of your net.
let's talk about that net. How do we build it? The formula is actually pretty elegant. It's just your point estimate plus or minus the margin of error.
That's all it is. The point estimate is your center point, your best guess. The margin of error is how far you reach out on either side to try and catch the truth.
So what determines how wide that reaches? What makes the margin of error bigger or smaller?
You've got three main levers you can pull. The first, and the most intuitive one, is sample size. We just call it N.
The number of people we talk to.
Right. The logic is simple. The more people you ask, the more information you have. The more info, the less mystery. So as it goes up, the margin of error goes down. Your net gets tighter.
But there's a catch, isn't there? I remember reading that if I double my sample size, I don't get double the precision.
No, you don't. And this is what breaks a lot of budgets. Because of a square root in a formula, it's not a linear relationship. To cut your margin of error in half, you have to quadruple your sample size.
Wow. So going from 100 people to 200 helps a bit.
But to really slash that error, you have to go from 100 to 400. It's a law of diminishing returns. That extra precision gets very expensive very fast.
Okay, so that's lever one. Lever two is the confidence level.
This is the big trade-off. How sure do you want to be? If you want to be 99% sure you've caught the truth in your net, you need a really, really wide net.
But if you're okay with only being 90% sure?
You can use a smaller, tighter net. You're accepting a bigger risk that the truth is outside your range, but you get a narrower, more precise-looking answer to give your boss.
So if I see a really narrow interval in a report, I should check the confidence level. They might just be cheating by only being, say, 80% confident.
Exactly. You can make your results look better by just lowering your standards of confidence.
Sneaky. Okay, and the third factor is variability.
Or standard deviation. Basically, how messy is the data itself? If everyone's answers are clustered together, variability is low, your net can be small. But if opinions are all over the map, your data is noisy. You need a much wider net to capture the average of all that chaos.
I want to pause on confidence level for a second. The text highlights a massive misconception here that I think I've been guilty of my whole life.
Oh yeah. Section 8.4 calls this out. Probably the most common mistake in all the statistics.
All right, lay it on me. If I calculate a 95% confidence interval of 7.42 to 8.18, does that mean there's a 95% probability that the true number is inside that specific range?
No.
But my brain really wants to say yes. It just feels so intuitive.
I know. Everyone's brain goes there.
Okay.
But no, strictly speaking, that's wrong.
Why?
Because the true number, the actual real average satisfaction of all 230 million people, is a fixed number. It's not a ghost floating around. It just is.
Okay.
So it is either inside your specific interval or it isn't. The probability is 100% or it's 0.
So it's binary. It's in or it's out.
It's in or it's out.
Yeah.
The 95% doesn't refer to the number. It refers to the method we use.
It's a method here.
It means that if we were to repeat this survey 100 times and we calculated 100 different intervals, we would expect 95 of those intervals to successfully capture the true number. We just hope the one we calculated today is one of the lucky 95.
That is a subtle but huge distinction. So 95% confidence is a grade on the process, not a probability for the numbers I just wrote down.
You got it. It's confidence in your tool, not in your specific results.
Okay. Let's talk about the tools. Z distributions and T distributions. This is where I think people get flashbacks to Stats 101.
It's way simpler than it sounds. It really just comes down to one question. How much data do you have?
And the magic number is 30.
30.
Mhm.
If your sample size N is 30 or more, you're in large sample territory. And thanks to something called the central limit theorem, we could assume everything is behaving nicely and normally. We use the Z distribution,
The classic bell curves.
the bell curve we all know and love. The source had that employee productivity case. They had 145 workers way over 30. So they used a Z-score of 1.96, which is the standard value for 95% confidence.
Predictable. But what if you don't have 30 people? The source had that new app beta test example with only 18 users.
Right. When you only have 18 data points, you're in the danger zone. It's a small sample. That means you can't be sure your little group is truly representative of everyone.
So you can't use the regular bell curve.
No, if you did, you'd be overconfident. Your interval would be too narrow for how little you actually know. So we use something called the T distribution.
How is the T different from the Z?
Visually, it just has heavier tails,
Heavier tails, so it's flatter.
flatter and wider. It pushes the boundaries of your interval out. It's the math basically saying, hey, you only asked 18 people. I'm going to force you to be more cautious and use a wider range.
Which is why in that beta test example, the interval was huge. It went from about 70 to 78.
Almost a 10-point spread.
Yeah.
That reflects the massive uncertainty from such a small sample. The T distribution protected them from thinking they knew more than they did.
So Z for big data, confident curves. T for small data, cautious curves.
That's a perfect summary.
Now, so far we've been talking about averages, mean satisfaction, mean productivity, but a lot of business isn't about averages, it's about yes or no.
Did they buy? Is
Right.
the part defective? Who did you vote for?
Right, proportions.
It's categorical data. And you can build confidence intervals for these too.
And the source had this great example on manufacturing quality control that really showed how this affects decisions.
The factory inspection case, yeah.
So they inspect 500 products, they find 32 are defective. Simple math, that's a sample defect rate of 6.4%.
And that 6.4% is your point estimate.
Okay.
Now imagine you're the manager and your boss's target is strict. Defects must be below 5%.
Well, based on the 6.4%, I'm in trouble. I missed the target.
You did. But is that 6.4% the whole truth? Or just a bit of bad luck in your sample? You need the interval. And when you calculate it, the 95% confidence interval is actually 4.25% to 8.5%.
Okay, let's read this like a manager. The low end, 4.25%, is below the target.
So it is possible that your true defect rate is actually fine. There's hope.
But the upper end is 8.55%.
Which is a complete disaster. It's almost double your target.
So can I, as the manager, go to my boss and say, we're meeting the target?
You can't. Because the interval contains values as high as 8.55%, you can't safely say you're compliant. The data is inconclusive, but it's leaning toward bad news. That upper limit is a flashing red light.
It defines the worst-case scenario.
It tells you you might be okay, but you are at serious risk of being way off. You need to investigate what's going on.
Now, a lot of this happens after you get the data, but smart managers use this math before they even start.
Yes. This is determining sample size. It's working backward, and this is where you can save your company a ton of money.
Because your boss doesn't just say, go survey people. They say, I need to know the answer to within plus or minus $15. How many people do we need to ask?
Exactly. You define the precision you need first.
Yeah.
The source used that beverage company example. They needed to estimate spending, and they needed a margin of error of exactly $15.
And they wanted 95% confidence.
Right. So you plug those goals into the formula, but you solve for N, the sample size. The calculation spits out 123.37 households.
And you can't interview 0.37 of a household.
No. So what do? Standard rounding rules say you round down to 123.
But that's a trap.
A huge trap. If you round down to 123, your sample will be slightly too small. Your margin of error will be slightly bigger than $15. It might be $15.02.
You failed the mission.
You failed the mission. You must always, always round UP to the next whole number.
So 123.01 becomes 124.
Always. 124 households guarantees you hit that precision target.
And this connects right back to cost. If a survey is $50 a person,
Now you know your budget. 124 people times $50. You need $6,200. And if your boss says, I've only got $3,000, you can look them in the eye and say,
then I can't give you the precision you asked for. The math doesn't work.
exactly. It stops the guessing game and makes it about resources and reality.
That's such a powerful tool. Okay, home stretch. Implementation, we're not doing this on paper anymore.
No, thank goodness.
Yeah.
We use Excel.
Yeah.
You use functions like confidence.norm or confidence T. You plug in your numbers, and it just spits out the margin of error.
Simple enough. But there are still pitfalls. We talked about the rounding down error. What else?
A big one is confusing standard deviation with standard error.
Ooh, they sound almost identical.
They do. Standard deviation measures the spread of individual data points, how different one customer is from the next. Standard error measures the spread of sample averages.
And the standard error is always smaller.
Much smaller. Averages are more stable than individuals. If you accidentally use the wrong one in your formula, your interval will be massive and completely useless.
And the other big mistake.
Using Z instead of T for a small sample. We just talked about it. It's an overconfidence error. You'll think you know the answer when you really don't.
It's that false confidence
It
again.
always comes back to that.
So let's zoom out. Why does this matter to the person listening right now, the non-statistician?
Because you are swimming in a world of data. Every day you see a headline. This diet improves health by 20%. 60% of people support this new law.
And we just accept the number. We think, oh, 60%. Fact.
We accept the point estimate. What a confidence interval teaches you is to be a healthy skeptic. It teaches you to ask the next question. What's the margin of error?
How big was the sample? Is that 60% or is it really a range from 50% to 70%?
Because a range from 50 to 70 tells a very different story than exactly 60%. It turns you from a passive consumer of data into an active questioner. It's about honesty. They define the limits of what we know.
That's a fantastic takeaway. The next time you see a poll or a report, look for the fine print. Look for that margin of error.
And if it's not there, you should ask yourself, what uncertainty are they trying to hide?
A great thought to end on. Without the margin of error, a number is just a point estimate masquerading as a fact. Thanks for diving deep with us.
My pleasure.